Dear Professor and everyone, today I'll be sharing the key findings from my research on machine learning and its connection to databases and data management. So this slide presents the outline of the key topics I'll be covering in today's research presentation. So now let's start with the big picture. Machine learning is a key part of AI that enables systems to detect patterns and make decisions not by following hard-coded rules, but by learning from data. We see it everywhere in fraud detection, recommendation engines, even language tools like chatbots. There are three main types of machine learning. Supervised learning, where models are trained on labeled data. Unsupervised learning, which finds hidden patterns in raw data. And reinforcement learning, where agents learn by trial and error through rewards. All of this is built on solid statistical techniques like regression and classification to help systems improve over time. But here's the thing, none of it works without good data. So now let's talk about why data is absolutely critical in machine learning. As the saying goes, garbage in, garbage out. Even the most advanced algorithm will fail if it's trained on poor quality data. Traditional databases also struggle with today's fast, messy, high volume data, which is why we need flexible architectures like NoSQL and data lake to keep up. And to manage the entire machine learning lifecycle from training to retraining, tools like ML Flow are essential. Models also need to evolve as data changes, something we call concept drift. So ongoing monitoring and adaptation is key. In short, the success of any machine learning system depends not just on the model, but on how well we can manage its data. So that we have seen how important data is to machine learning, let's dive into what kind of data we actually need. So first, there's the question of structure. So structured data like rows in a database works well for traditional models and is common in supervised learning. Unstructured data like text, images, or audio is messier but vital for tasks like language processing or image recognition. And then there's semi-structured data like JSON or XML, which sits in between. In reality, machine learning systems today need to handle all three. That's why hybrid data architectures are critical, especially in fields like education or voice assistance, where formats vary widely. So we have next we have the three V's of data. Volume machine learning needs lots of data. Variety, that data comes in many forms, and velocity, and it's often a drive fast, especially in real-time application like fraud detection or autonomous driving. These three factors shape how we design systems that can scale, adapt, and make decisions quickly. But most importantly, none of this matter if your data is low quality. Noisy labels, missing values, or formatting errors can cripple even the best models. And in high-stakes fields like healthcare, the cost of poor data is even higher. So we use data quality tools to catch and fix the issues because in the end, high-quality data beats high-volume data every time. So now let's talk about the backbone of any machine learning system, the database and storage architecture. Traditional relational databases, while reliable and ACID compliant, simply wasn't built to handle the scale and messiness of modern machine learning data. They work great for structured data, but struggle with unstructured format and real-time demands. That's where big data tools come in, things like NoSQL, distributed file system, and NewSQL. These systems are designed to store and process massive volumes of diverse data using horizontal scaling and flexible schemas. And even though newer tools dominate, SQL still plays a key role in enriching systems and offering a familiar query interface. To support today's machine learning needs, we move toward modern data infrastructure systems that are scalable, modular, and built with automation in mind. Platforms like Meta ML Stack or Chase CI support real-time workloads, while domain-specific solutions enable high throughput, pipelines, and structural flexibility for specific use cases. Finally, we can't forget pipelines and data access. ETL and ELT patterns transform data for machine learning. Real-time access is critical for tasks like fraud detection or chatbots, and APIs from AWS Lambda to ABI gateways now tie it all together, automating ingestion, prediction, and deployment in a unified workflow. So the message is clear: if your architecture can scale, adapt, and automate, your machine learning system will fail behind. So now, so far we have focused on storing and accessing data, but now we take it a step further, integrating machine learning model directly into databases. This is a major architectural shift. Instead of constantly moving data between storage and machine learning tools, we embed models directly inside the database. This reduces latency, simplifies pipelines, and enables real-time inference and in-database analytics as highlighted recent work by Ruska and others. Modern SQL systems are also evolving. They now include native machine learning capabilities such as predictive queries and user-defined functions for tasks like forecasting or anomaly detection. Plus, they integrate directly with machine learning framework, making the workflow far more streamlined for data teams. We are also seeing advanced architecture emerge. Think learnable databases where machine learning have optimized query planning and indexing, or array databases and social AI infrastructure with support mixed structured and unstructured machine learning workloads at scale. Of course, integrating machine learning into databases isn't without challenges. They have to manage things like resource contention, versioning, and model explainability, especially when deploying at scale. But the potential payoff is huge. Today, databases don't just store data, they become part of the end-to-end machine learning lifecycle, supporting for feature stores, model registries, and even monitoring. So instead of machine learning being an external process, it's becoming a built-in capability, and that's a game changer. So now that machine learning is being embedded into databases, let's look at the real-world impact, both of the opportunities and the trade-off. On the opportunity side, the benefits are compelling. This improves decision making by reducing the lag between data collection and prediction. Real-time analytics for instant predictions is essential in dynamic settings like fraud detection, operational efficiency by eliminating costly data transfer from systems, personalization with output tailored in real time to user behavior, and automated pilots where training, validation, and deployments are continuous. So the result is smarter, more adaptive system with less manual effort. But this doesn't come without limitation. Bias and fairness risks if training data lack diversity, strict privacy regulations, especially in sensitive domains like healthcare, and high infrastructure costs for supporting real-time machine learning, and concept drift where model derail as data evolves, and the need for explainability and governance, especially in high-stake applications. So the key takeaway is successful machine learning databases integration demands not only technical strength but also ethical, scalable, and well-governed design. So to get wrap up, the key message is this: machine learning and data system are inseparable. No matter how powerful a model may be, its performance, its ethical impact ultimately depends on the quality of effective machine learning, um, the quality of the data it learns from, and the infrastructure it runs on. This research reinforces that view, showing how effective machine learning cannot exist without a robust data management and well-integrated system. Integrating machine learning with a modern database is essential for achieving a real-time responsiveness, scalability, and reliability. Furthermore, emerging trends such as federated learning and auto machine learning illustrate how the future of machine learning is being set by privacy, automation, and broader accessibility. In the end, advancing machine learning isn't just about better models, it's about building smarter, more resilient data systems to support them. Thank you for your attention. So preferences list are below. Thank you.